In the second part of the Unit G review, we're going to look at function operations and composite functions. What we are doing in this section is we are taking functions and putting them together to create new functions. We could be putting them together using operations, which includes adding and subtracting and multiplying and dividing. We also sometimes are taking functions and putting one function inside another function, which is referred to as a composite function. Sometimes we are wanting to graph these new functions. Sometimes we just want values for the new functions. Sometimes we want the equation of the new functions. There's a number of different kinds of questions that we can see in this section. What we do is we need to pay very, very close attention to the notation so that we know whether we are adding, subtracting, multiplying, or dividing, or finding a composite. And the other piece of information that we need to keep track of is the domain of our resulting function, because they are going to be coming from a number of different types of functions. For this review, I am primarily going to be looking at putting together polynomial functions and some radical functions and a bit of rational functions. But keep in mind that we could use any of the functions that we talked about in Math 30-1. So we can put together logs, exponents, we can put together trig functions and a mixture of those. So just keep that in mind, that with this review, I'm not going to look too much at like a trig function or a log function being added together, composites, but they would follow the exact same rules that these ones do. Let's have a look at number one. Number one is actually a multiple choice question. So it says, from the graph, what is the value of f minus g at 2? Okay, so f minus g means we're taking the function f at x and subtracting g at x, and we are doing that at a specific x value, which is 2. So we could actually rewrite this as f at 2 minus g at 2. So please keep in mind, this doesn't mean f minus g times 2. It's function notation, so it's f minus g at 2. F at 2 minus g at 2. So let's go to x equals 2 and let's find those y values. F at 2 is 3. G at 2 is -1. 3 minus a -1 is 3 plus 1, which is 4. So our answer would be D. Question 2, given x squared plus 2 and g at x equals x minus 5, which equation represents h at x, which is f plus g at x? So we're not looking for a value in this case. We're looking for the, oh, sorry, let me just go back. And notice that when I talk about adding and subtracting at a certain value, we're adding and subtracting the y value. So the x values sort of remain the same, whereas our y values are the ones that we end up putting together. Okay, question 2. We are trying to find the equation of our function, and f plus g at x means the same as f at x plus g at x. And we just have a nice quadratic and a nice linear that we're going to add together. So x squared plus 2 is f at x, plus g at x is x minus 5. And I always like to start by putting them in brackets, because if this is subtraction, it's going to end up affecting both terms of our second function if it has multiple terms. So I always substitute by putting it in brackets first, and then I remove the brackets and collect like terms. In this case, we would have x squared, we'd have a positive 2 and a negative 5, which is -3, and we have a positive x. So x squared plus x minus 3. So our answer here would be B. Very straightforward. Put the two functions together, collect like terms. So even if we had trig functions or log functions, it'd be the same thing. We would just add them together and then simplify. Question 3 says, let f at x equal x minus 1 and g at x be x squared minus 1. Determine the non-permissible values of f over g at x. So f over g at x just means f at x over g at x, which means x squared minus 1 is going to be in the denominator. So our non-permissible values are going to come from where g at x is equal to 0. So x squared minus 1 is equal to 0. That means x squared is equal to positive 1. when we square root both sides, we consider both the positive root and the negative root. So x cannot equal plus and minus 1. There's our non-permissible values. So really, while that is a division question, it's also just talking about rational functions and understanding what the non-permissible value is of a rational function. Question 4, if f at x is the radical function 3x minus 1 and g at x is x squared, what is the domain of f at x over g at x? Okay, so let's talk about domain. When we are doing any of the operations, so adding, subtracting, multiplying, and dividing, the domain comes from the common domain of each of the individual functions. So in this case here, this is a radical function. We know that we cannot take the square root of a negative number. So to find the domain, we take the radicand, we make it greater than 0, and we isolate x. So our restriction or our domain for f at x is going to be that x must be greater than 1/3. G at x is just this lovely quadratic. It's very, very simple. Its domain is x is an element of the reals. So if I look at these two domains, the common domain would be x is greater than 1/3 because that's where they both exist. So that's where we're going to start. So our domain for sure is going to be x has to be greater than 1/3. And if we were just doing adding, subtracting, or multiplying, our domain would be done. With dividing functions, we also need to think about where is the denominator 0. So x has to be greater than 1/3, but we also have to recognize that x, and this should be equal to, we also recognize that x cannot equal 0. Now, it actually really doesn't come into play because if this is our restriction, it's already not going to be equal to 0. So our end domain here is going to be C, x is greater than 1/3. So again, just to reiterate, when we're adding, subtracting, and multiplying, the domain of our combined function is going to be the domain that's common to the individual functions. Same with division, but we also must look at where the denominator is 0. Let's go up to the top here. So here we are given two functions, root x and 4 minus x. And what we want to do is we want to match each of the combined functions with what the graph would look like. So let's start with f minus g. F minus g means the same as f at x minus g at x. So that would be root x minus 4 minus x, which we need to be careful because when we remove the brackets there, that's going to become root x plus x minus 4, root x plus x minus 4. So it's going to be kind of a radical function. And so right now I'm going to think that it's probably going to be either A or D because those are the only two that look somewhat sort of radical-ish. And I'm going to lean towards D because it has that kind of radical form. I'm not quite sure, so I'm not going to answer that yet. F plus G at x. So this is going to be root x plus 4 minus x. Or we could write it as root x minus x plus 4. And again, that's going to be the difference here. This guy has a positive 4 as its constant. This has a negative 4 as its constant. So that kind of settles it for me that D goes with equation I and A is going to go with equation 2. Okay, again, it's kind of a radical function, so we can tell it has that shape, and it's the positive 4 that is clinching it for 2, that is going to be A. F at x, this, see how they're just right tight together? This implies multiplication. So what we have is root x times 4 minus x, which would be 4 root x minus x root x, which if we graph that one ends up being this guy right here, which should be B right here. So this would be the third one. And we can also graph them on your calculator and see which one it is. And then F over G, I mean, it kind of gives it away that this looks rational, makes sense. There's a vertical asymptote there. So we could probably have picked C for 4 without doing any work. But let's just have a quick look at it. It would be, I'm going to use a different color so we can differentiate here. It would be root x over for minus x, which then you can see we've got that non-permissible value at 4, and this has that vertical asymptote at 4. So it makes sense. So there you get a chance to see all 4 of these functions in, so all 4 operations with 2 functions. Now, if we were going to talk about the domain here, I know it doesn't ask, but if we were going to talk about the domain, we would go back to the original functions. So this guy's domain is x is greater than or equal to 0. This guy's domain is x is an element of the reals. So our combined domain would be x is greater than or equal to 0 for these 3, which we can see, x is greater than 0, x is greater than 0, x is greater than 0, except for 4. 4 has the added part, x is greater than 0, but also x cannot equal 4. So that's why with graph letter C, x is greater than 0, and we have that vertical asymptote at 4. Question 6 is a little bit different. In question 6, we're not given a graph. All we're given is a table and asked to do some evaluation. So again, this is basically like finding the y values on the graph and then just putting them together according to whatever operation we're given. So for A, we have g at x, g times f at 6. Keep in mind, this means the same as g at 6 times f at 6. And we can find both of those values from the table, just like we would be able to find both of those values from a graph. G at 6 is 3, f at 6 is 5, 3 times 5 is 15. So that would be our answer there. And if we were graphing it, then at our function at x equals 6, we'd have a y value of 15. F over g at 1 just means the same as f at 1 over g at 1. So let's go up to x equals 1. F at 1 is 3, g at 1 is 6, and then that reduces to 1/2. So if we were graphing the graph of f over g at 1, or f over g at x, it would go through the point 1, 1/2. Now let's look at this. This isn't multiplication. I know it looks like f, and then because there's brackets, it looks like it's multiplication. This is not. So for the first time, we are seeing what's called a composite function. What this means is it means that g at x is actually being put inside f at x. So it's kind of like g at x has become the x or the input for f at x. So let's just talk a little bit about notation. For multiplication, if we have f and g right next to each other with nothing in between, that's multiplication. So f g at x, or f at x, g at x, or with the closed dot, f times g at x. That's all multiplication. For a composite function, so that instead of thinking of just putting them together by multiplying, but putting one function inside of the other function, it looks like this, f bracket g at x. So if f and g are separated by a bracket or an open dot, so f open dot g at x. The closed dot or solid dot implies multiplication. An open dot, which is not an O, it's just an open dot, implies composite. So pay close attention. This again, composite function. What does that mean? It means that the 2 is going to act on the G, and then the answer to that is going to act on the F. So we work from the inside out. F at G at 2, well, let's find out what G at 2 is. G at 2 is 3. So I'm going to evaluate G at 2. Now I'm going to evaluate f at 3. So the 2 acts on the g acts on the f. F at 3 is 4. So our final answer here would be 4. This is also implying a composite because we have that open dot. This is the opposite though. See how g is listed first and f is listed second? That means the 5 is operating on the f, and then the answer is operating on the g. So we could write this as g at f at 5 if you were more comfortable with that. So f at 5, we can evaluate that's 2. The 5 operates on the f, and then the result operates on the g. G at 2 is equal to 3. So a little bit different with composites, versus operations. We have two more here, f minus g at 4. So this means the same thing as f at 4 minus g at 4. So f at 4 is 2, g at 4 is 1, 2 minus 1 is 1. And then this is kind of weird, a composite of itself, g at 1. Again, open dot is not multiplication, it's composite, g at 1. That means the 1 is going to operate on the g, we're going to get an answer, and then that answer is going to operate on the outer g. So g at 1 from the table is 6. So g at 1 is g at 6. And then g at 6, we can see from the table, is equal to 3. So there's our first interaction with a composite function. Okay, next one, number 7. Given the functions 1 over x as f at x and g at x is 1 over x minus 1, determine the equation of the combined function h at x and then state the domain. Okay, so in this case, h at x just comes from adding f and g together. So that would be 1 over x plus 1 over x minus 1. We never want to just leave our functions like this. We always want to put them in the most simplified form. So in this case, to get a simplified form, I need a common denominator. That common denominator is going to be x times x minus 1. That means that I have to multiply this numerator by x minus 1, plus I have to multiply this numerator by x, removing the brackets and collecting like terms. This gives us 2x minus x over, and I'm going to expand down here, x squared minus x. So please make sure that if you can simplify your functions when you're doing the operations, you simplify them. We always want to give answers in the most simplified form. Okay, now we want the domain. So let's remember where our domain comes from, where we're adding. It comes from the domain of our two originals, where they are in common. So the domain of f at x here is that x cannot equal 0. Our domain for g at x is that x cannot equal 1. That means our common domain is going to include both of those non-permissible values. So our domain in set notation is the set of all x such that x cannot equal 0 and 1. Otherwise, x is an element of the reals. And that would be the same domain if we were subtracting and if we were multiplying and even if we were dividing. Question 8. If f at x is equal to x plus 1 and g at x is equal to x squared plus 1, h at x is equal to 1 minus x. So we've got a couple of different things going on here. Determine each equation. Q at x is equal to f at x plus h at x. Okay. F at x is x plus 1. H at x is 1 minus x, and we always simplify, so collecting like terms, we're going to have x minus x, which is 0, 1 plus 1, which is 2. Done. Done. That would be our answer for that one. This one, be careful, g at f at x. So this is a composite function, so it doesn't mean we are multiplying, it means we are taking f at x and putting it inside g at x. So we are taking this whole thing of f at x and taking it and putting it in for x in g at x. Now we need to be careful because that x is squared. So here's what p at x is going to be equal to. It's going to be equal to, instead of x squared plus 1, it's going to be equal to x plus 1 all squared plus 1. Why did the x become x plus 1? Because f at x is x plus 1. And we are determining g at f. Keep in mind that when we switch f at g, if I was to write it as f at g at x, that means something different. F at g at x means we would be taking the whole thing of g at x and putting it in for x in f at x. So the order of the f and the g are very important. The one that's listed second is the inside function. It's the one that's being put into the outside function. Okay, but let's get back. We want to simplify where we can. So this question can be simplified because we can do some distribution. So x squared, or sorry, x plus 1 all squared. Remember that that means the same as x plus 1 times x plus 1. So when we distribute, we're going to get x squared plus 2x plus 1. We still have the plus 1 sitting on the end. So collecting like terms, x squared plus 2x plus 2 would be our composite function there. Question 9, consider the functions root x plus 3 and x squared. Determine an equation for h at x, which is f over g, and state the domain. Okay, great. H at x equals f at x, x plus 3, over g at x, x squared. And remember when I keep saying we want to make sure we want to simplify this when we can? This is as simplified as this gets. So in this case, I'm just going to leave h at x like that. It's not like the ones above where we can do some expanding or get a common denominator or collect like terms. This is as simplified as h at x is going to get. So we're going to just leave it like that. Now we want to state the domain. So again, when we have division, our domain is going to come from the individual functions and where the denominator is equal to 0. So here our domain is that x must be greater than or equal to -3 because it's radical. We can't take the square root of a negative number, so x has to be greater than -3. And here, g at x, our domain would be x is an element of the real. So if we were just doing adding, subtracting, or multiplying, our domain would end up being just the x has to be greater than or equal to -3. That would be our common domain. But because we have division, we have the added part that g at x can't equal 0. So we have to add that into our domain. So in set notation, our domain is going to be the set of all x such that x is greater than or equal to -3, comma, which means and x cannot equal 0. Otherwise, x is the element of the reals. If this was just adding and subtracting or multiplying, we wouldn't have to worry about the x can't equal 0 part. But because it's division, we need to be aware that we can't have a denominator of 0. Number 10. Number 10. If h at x is equal to f at x over g at x, and f at x is x cubed plus 6x squared plus 11x plus 6, determine g at x if f at x is this. So I like this question because you have what the combined function is. You need to determine what one of the original one is. So here's what we're going to do. We're basically going to simplify. So we have h squared, which is x squared, plus 3x plus 2. That came from f at x, x cubed, plus 6x squared, plus 11x plus 6, over g at x. What we want to know is, we want to know what g at x is. So if I rearrange this equation, g at x is equal to x cubed plus 6x squared, plus 11x plus 6 divided by h at x. So just by rearranging the equation to isolate g at x, that's what we get. Now we want to simplify this, and in order to simplify, we need to factor. So factoring the denominator, that's not bad. Two numbers that multiply to give us 2 and add to give us 3 are going to be 2 and 1. Now, factoring the numerator, though, that's a good review of Unit C of polynomials. Okay, so how do we factor a cubic polynomial? I'm just going to do this little side calculation in a different color. We want to start with our potential zeros, which come from our constant. So plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6. And what we can do is start substituting them into the function to see what is actually going to give us a 0. And what I already know is I know that f at -1 gives us 0. F at -1 gives us 0. If I plug -1 in here, I'm going to get -1 plus 6 minus 11, which is going to be -12, plus 6 gives me positive 12, which is 0. That tells me that x plus 1 is a factor. And so what I'm going to do is synthetic division. So I am going to use the put the 1 in there, or put the root in there, put the -1 in there, and write our coefficients, which are 1, 6, 11, and 6, and divide synthetically. Bring the 1 down. 1 times -1 is -1, and I'm going to add. That gives us 5. 5 times -1 is -5. We're going to add, and we get 6. 6 times -1 is -6, and we add, and we get 0. So that's good. That means that our remaining factor comes from this, which is going to be a quadratic. So currently we have x plus 1 times x squared plus 5x plus 6. We can easily factor that quadratic. X plus 1, this is going to be two numbers that multiply to give us 6 and add to give us 5, will be +2 and +3. Okay, so let's put that in there. That's a little side calculation, a little quick review of how we algebraically factor a cubic polynomial. So x plus 1, x plus 2, x plus 3. That means that the x plus 2 will take out the factor in the numerator. This will take out the factor in the denominator. We're just left with x plus 3. So g at x is equal to x plus 3. So here's the thing with this section of content, is so much of it has to do with the other pieces from the course. The only thing that we did here that actually comes from this chapter was setting up the division. Everything else came from our polynomial section. So this composite and combining of functions truly helps you review a lot of the other content in the course. Almost done. Question 11. If f at x equals x squared, h at x is x plus 1, g at x is, look at this, 3 times f at x at h minus 5. Determine an equation. Okay, wow. Let's start in here. F at x plus h means, see how h at x is our inside? F at x at h, sorry. So see how h at x is our inside function? That means we're taking this whole thing of h at x and we are putting it inside this guy right here, f at x. So we'll start with that bit. F at h at x is going to be, instead of x squared, x plus 1 squared, which when we distribute becomes x squared plus x plus 2x plus 1. But notice that we have the 3 and we have the 5 in front. So what we need to do is we need to keep going here. We can do the 3 first. So we're going to take our composite function, which we just found, and we're going to multiply it by 3. So 3 f at h at x is going to be 3 times x squared plus 2x plus 1, which is going to give us 3x squared plus 6x plus 3. Last thing we need to do is subtract 5. So we can do that pretty quickly just by subtracting 5 at the end. So 3 times f at h at x minus 5 is going to be the 3x squared plus 6x plus 3 minus 5. That gives us 3x squared plus 6x minus 2. There is our equation. Describe g at x as a transformation of f at x. So we can kind of see that for sure. We've multiplied f at x by 3. We've also subtracted 5. So I know for sure that we will have a stretch about the x-axis. That's our vertical stretch by a factor of 3. Because we subtracted 5, I can see that we would have a translation of 5 units down. Now, the f at h at x, I'm going to go to this right here, x plus 1 all squared. Before we distributed that, notice that it was just x plus 1 all squared, which from x squared to x plus 1 all squared means we moved it to the left. So from the f at h at x, that actually is the same as moving it, a translation of 1 unit to the left. So that would be our transformations there. Question 12, consider the functions f at x equals x squared minus 5 and g at x equals root x plus 2. Determine f at g at 7. So this is kind of like the table question that we did on the previous page, but instead of using the table to evaluate, we're going to use the functions. So the 7 operates on the g. Let's start there. G at 7 will be the square root of 7 plus 2, which is going to be the square root of 9, which is 3. So G at 7 is 3. Now what we're going to do is substitute 3 for the G at 7 and evaluate f at 3. F at 3 is 3 squared minus 5, which would be 9 minus 5, which is 4. Alternatively, what you could do, this would probably be the long way, but you could get an equation for f at g at x. So you could take g at x, plug it into f at x and get the simplified function, then substitute in the 7. You'll still get 4. It's totally up to you if that's the steps you want to take. And then finally, question 13. If h at x is f at g at x, again, open circle means composite function, determine g at x. So again, here is where we have the composite function. We have what the outside function, we need to figure out what the inside function is. So f at g at x is giving us h at x. So in this case, what I would do is f at x is x squared. So f at g at x would be g at x squared. And that gives us h at x, which is x minus 4. So we end up setting it up, substituting in and setting it up just as an equation. How would we isolate g at x then? Well, we would take the square root of both sides. We just need to be careful. When we actively take the square root, we need to consider the plus and minus root. So g at x in this case would be equal to plus and minus root x minus 4. We can set up the same way here. We know that f at g at x in this case also gives us h at x. Here's our f at x. F at x is x squared minus 4. So f at g at x will be g at x squared minus 4. Just replace your x with g at x. And that gives us our value of h at x, which is x squared plus 6x plus 5, which actually just sets up a nice equation for us. We just need to isolate g at x. I'm going to start by adding 4 to both sides. So g at x is still squared. I'm just going to add the 4 to both sides. So x squared plus 6x plus 9. And then again, because we want to solve for g at x squared, we're going to take the square root of that. So g at x is equal to plus and minus root x squared plus 6x plus 9, which you might notice, you might not, this is a perfect square trinomial. So this is actually can factor into x plus 3 all squared, which gives us plus and minus x plus 3. So an interesting way to deal with composite functions where you know what the composite is, you're missing the inside function, so you have to solve for it. So a few different types of questions there, some where we were evaluating, some where we were finding the equations, some where we were talking about the domain. And so what you need to do now is make sure that you have completed your Unit G assignments and go through some of these review, and you'll be able to be ready for your Unit G quiz.